This is a story of molten rock, wind and fire, of creation and destruction. It is the story of the astonishing forces that repeatedly reshape our world. They work together, are mutually dependent, and enhance each other. Scientists are working to understand these interrelationships so that we can be better protected. Because if the Earth were an apple, its crust would be no thicker than the skin, and on it, we erect skyscrapers and settle in the shadow of fire-spitting mountains. Volcanoes, earthquakes, and storms, they'll be with us always. So we have to protect ourselves from their violent tempers. Because although its beauty is incomparable, our wild planet is no gentle giant. When the Department of Commerce propeller plane is rolled out of the hangar, it does not bode well for the people of Florida, or even for those as far away as New York. A hurricane currently causing death and destruction in the Caribbean could soon bear down on them too. The crew on board the aircraft is embarking on a veritable kamikaze mission. They are destined for the hurricane itself. As it moves on its relentless course towards the U.S. mainland, residents of the coastal regions begin implementing their evacuation routine. But to be able to predict how the monster storm will develop, where exactly it will make landfall, and how it will take shape, the pilot must steer his aircraft right into the eye of the storm. More precisely, the eye wall. This ring of vertical clouds, extreme rainfall, and storm winds surrounding the calm eye reveals the real force of the monster. The aircraft navigates several times through the wall. Only by determining the exact force of the eye wall winds can a reliable prognosis on the hurricane's development and course be made. Every 2 seconds, the sensors take air pressure, humidity, and wind velocity measurements. Meanwhile, the stormy weather has begun to thrash the Florida coast. Whoever has failed to bring their boat to safety in time is in for a nasty surprise. Areas most at risk have long been evacuated. Where these places will be and who should leave them are prognoses made by the National Hurricane Center in Miami. James Franklin and his team work day in, day out to be able to forecast the development of a hurricane more precisely.
Hurricanes are very different in terms of their shapes. We have some that are maybe 60, 70 miles across and others that are 600 or 700 miles across. So there's a tremendous scope of the size of these storms. To some extent, size doesn't change very rapidly. Storms that start small tend to remain small, storms that are large tend to remain large. But the details of the structure is what's really difficult.
But the peril lies in these very details. They ultimately determine the scale of damage and loss. And not only can hurricanes bring large-scale devastation, they also occur with far greater regularity than earthquakes or volcano eruptions, and thus cost more human lives all told. But what exactly are storms? What happens precisely when a storm is brewing? The surface of the Earth is covered by cities, deserts, green forests, and bodies of water. The air above these different areas is warm to varying degrees. For example, over land, the air warms during the day more quickly than over water. The warmer air masses rise more quickly, which means that the air pressure is higher in the skies above land than above the sea. Wind equalizes this pressure differential, always moving from the higher to the lower pressure. As wind moves high above, from the land to the sea, the air just above the surface flows in the opposite direction. A sea breeze is born. The wind equalizes varying pressure levels globally. As the planet rotates, air masses on their way from high to low pressure areas are sent into a spin. In the northern hemisphere, the winds are diverted to the right, in the southern hemisphere to the left. Gigantic rotating storm systems are sent racing across the Earth. When a storm system like this has reached hurricane force and is heading for the east coast of the United States, it's time for the hurricane hunters to take off. Because without the data gathered at the center of the storm, it would be impossible to calculate the development of a hurricane in progress. Jim McFadden is responsible for the whole operation.
We don't know what's going on out over the ocean. You've got to get an airplane out there, and it's got to make drops, and it's got to collect those data, and you got to get those transmitted off the airplane so that they can go into the models.
In October 2012, those models signaled a red alert for New York City and the entire eastern seaboard. Hurricane Sandy was already raging in the Caribbean, leaving a high death toll and horrible destruction in its wake. Would the superstorm hit the coast at full force or run out of steam like Hurricane Irene the year before? It had traveled offshore. The forecasted landfall and flooding never materialized. Will the mayor's large-scale evacuation effort again prove unnecessary?
The time for evacuation is over. Everyone should now go inside and be prepared to stay inside until weather conditions improve, which won't likely be until Sunday afternoon.
But it soon became clear that the city wouldn't be getting off so lightly this time. The hours of anxious apprehension followed, waiting for Sandy to strike with all her might. 95-mile-per-hour winds battered New York City, and a record deluge flooded entire neighborhoods. Meanwhile, Sandy was being tracked in real time from outer space. This data was added to that of the hurricane hunters and of the 20 radar stations along the East Coast. All of this information converged at the National Hurricane Center in Miami, where all tropical storms 250 kilometers from the coast or closer are observed live. The goal is to be able to warn the public earlier and to better coordinate evacuation efforts.
You want to do your best job. You want to make the best forecast you can every time you sit in that chair, because you know that so much depends upon it.
More than 47 million people from Texas to Maine are in harm's way of hurricanes, and their number is growing. The incidence of typhoons and cyclones is also increasing worldwide. But what's the difference between a hurricane and a typhoon, and what constitutes a cyclone? The answer is simple. They are different regional designations for the same phenomenon. A hurricane over the Atlantic is a typhoon when it rages in the western Pacific, and cyclones plague the Australian coastal region. There are two prerequisites for hurricane formation: an ocean temperature of over 26 degrees Celsius and powerful trade winds that sweep the Earth's surface. These precise conditions are only met within a narrow strip between the 5th and 20th parallels, north and south. Between early June and the end of November, ocean temperatures are high enough to allow sufficient water to vaporize. The resulting humid, warm air rises upwards, where it is condensed to clouds, which are then made to rotate by the trade winds. When the winds in the eye wall reach a speed of at least 118 kilometers, the phenomenon is called a hurricane. That's the current status of research. But it's recently been confirmed that about 90% of all hurricanes that bash the U.S. East Coast are not born at sea after all. Over the hot soil of the African continent, tall tropical thundercloud towers form, rising way up into the atmosphere. The trade winds that continuously sweep across these latitudes westwards are swirled by the cloud towers. The still small tropical vortexes fuel up with energy over the warm water off the coast of West Africa. Once on the move, the air masses continue to gather force, becoming so powerful on their trip across the ocean that landfall brings widespread devastation. But there is yet another great unknown in the equation: clouds. Without clouds, there can be no hurricanes. But very little research has been done to date on how precisely clouds come into being. In the cloud simulator at the Leibniz Institute for Tropospheric Research in Leipzig, Germany, scientists are trying to pinpoint the conditions that allow clouds to form. In addition to playing a decisive role in storm systems, clouds are also an important factor in climate models. But because the process of cloud formation has not been well enough understood, it has been underemphasized or even left out of such models. Aerosols, a mixture of fine suspended particles, solid or liquid, play a significant role here.
One of the great uncertainties in current climate forecasting and in the climate models used to make such predictions is the interaction between aerosol particles and clouds. One such interaction is that aerosol particles cause the clouds to freeze or influence the freezing process. Our results make a contribution to moving the forecasts or the equations in the models a bit closer to reality.
Impurities in the air, known as cloud condensation nuclei, are required to transform water into ice crystals, thus creating clouds. The Leibniz researchers are experimenting with a wide variety of particles to find out how they control the formation of clouds. The Sahara is the major source of atmospheric mineral dust. At the same time, this desert also has the power to nip the development of cloud systems in the bud and thus prevent hurricanes.
When a heavy load of dust from the Western Sahara is conveyed towards the Atlantic Ocean, it disrupts the development of a hurricane that happens to be forming there at the same time. It's simply the arid air that comes with this dust wraps around the hurricane, basically cutting it off from its humidity supply. That means that dust outbreaks in the Western Sahara inhibit hurricane development.
Only the whirlwinds that make it through this package of dusty air are able to develop explosively, embarking on their journey across the Atlantic. So without the huge supply of dust from the Sahara, prospects would be grim for the east coast of the USA. Miami is especially at risk. Every other year, a powerful tropical storm sweeps through the coastal city, and every 5 years, it's hit by a hurricane. The next is now anxiously awaited. But in Chester County, South Carolina, they're busy making their own superstorms. In the Business and Home Safety Research Center's Hurricane Simulator, they're preparing for a building test. Cameras are installed in and around the test building to document every phase of the tests.
When we turn the fans on and we go up to full speed, it's like turning on the electricity for a town of 9,000 homes.
More wind is produced here than produced by the water at Niagara Falls. The two test participants stand on a pivoting platform so that they can be exposed to winds from all different directions. Cannons help to simulate wind-whipped debris. The hall has to be cleared just before the test starts. The 105 fans can create winds of up to 200 kilometers per hour and Category 3 hurricanes. But the installation does more than just pure power. Data taken from real hurricanes can also be programmed in and simulated. Blowers that run forwards and back can generate gusts and all sorts of wind variations. When the windows have been blown out and the winds press on the roof and walls from within, the structural engineering is especially challenged. The conventional construction style soon displays its weakness. Before the video images are reviewed, every stone is turned and every bit of building material checked for damage. Lightweight construction in the United States has repeatedly led to unnecessarily severe damage, which could often have been avoided with minor reinforcements.
We've seen this kind of damage so many times out in the field after a hurricane, and to be able to put it in a controlled environment and to be able to communicate to people that for a few $100s, maybe $3,000 total difference between the two buildings for all the things we did. You have one building that's, you replace that one window, you're back in business. The other building is going to be demolished.
And the houses aren't only exposed to wind power. Hurricane companion phenomena such as rain of fire, glowing embers, and all sorts of foreign bodies can also be fed into the wind currents. These experiments come too late for the people who lost everything when Sandy hit. The hurricane left at least 142 dead in its wake, 72 of them in the United States alone. On the morning of October 29th, over 8 million people were without electricity, many for several days. The total damage from Sandy has been put at $50 billion. Considerably less economic loss was caused by the outbreak of Iceland's Eyjafjallajökull, when volcanic ash grounded international air traffic for days on end. But the eruption brought another surprise. Lightning shot from the ash cloud, lighting up the night sky. Because it turns out that big ash clouds behave exactly like thunderclouds. They are formed when warm, humid air rises up into the atmosphere, expanding as it goes, and then cools down until ice particles form. The warmth set free by condensation creates a strong updraft that pulls the little ice particles along with it. By colliding with each other, they become charged. Due to their greater weight, here large negatively charged ice pellets are stored in the bottom part of the cloud. Lightning equalizes the tension. Hurricanes are to summer what blizzards are to winter. Statistically, they are less deadly, but are nonetheless able to bring whole regions of the country to a virtual standstill. Because the American continent has no major mountain ranges running from east to west, cold air from the polar regions can reach far into the south. Warm southern air is sucked in, supplying the huge amounts of humidity needed to cover the country in snow and ice. February 2nd, 2011 wasn't just Groundhog Day in the US. An extreme blizzard was also wreaking havoc from northern Canada all the way to New Mexico. Millions of people were left without electricity. In Europe too, severe storms and floods are becoming more common. Interstate communications proved deficient when eastern Germany was swamped in heavy floodwaters. So, in 2002, state and federal governments established a joint situation center. Since then, all German disaster relief efforts, both domestic and cross-border, are coordinated from here. In early 2007, damage limitation work began here 72 hours before Kyrill struck its massive blow. Site plans and prognoses were compiled and communicated to relevant domestic and international authorities. Resources such as sand sacks, tents, and helicopters were brokered from here to avoid shortages at key points. And new challenges will face the center in the future as the number and severity of European blizzards increases. They mostly develop over the North Atlantic, from where they move towards northwestern Europe, where cold air meets warm air, high pressure meets low pressure. The forces that are then unleashed shave entire forests bare and submerge cities in flash flooding. Public infrastructure collapses. Geophysicist Szymon Widowiński discovered that the heavy rains that the hurricanes have in their luggage can also have very different surprising consequences. Extreme precipitation, such as in the case of tropical storms, flushes huge amounts of earth into the ocean, thus changing the pressure ratios in the ground. Rock, long under pressure far below, is suddenly relieved of this pressure and begins to stretch its legs. Events in 2010 in Haiti showed what dramatic consequences such a change in pressure can have. The most devastating earthquake of the 21st century cost 300,000 people their lives and left over 1 million homeless. 1.5 years earlier, gigantic hurricanes had plagued the region, causing major landslides. Huge amounts of earth that had piled up were washed into the sea. Though the data from Haiti is sparse, Widowiński is certain that the storms triggered the earthquake.
We started the research in Haiti, but there is very little data in Haiti, both regarding earthquakes and hurricanes. So we found that a similar phenomena occurs in Taiwan, and to do that, to understand the relation between these two phenomena, we analyzed the wet typhoon data set over the past 50 years and the data set of earthquakes in Taiwan. And we found that there is very significant relations in the timing of earthquake after these wet typhoons.
In August 2009, Typhoon Morakot raged across Taiwan. Gigantic amounts of soil thus found their way from the mainland into the sea. Only a half a year later, the strongest quake for more than a century rocked the southeast of the country. 85% of all major quakes in Taiwan hit within 4 years after a typhoon, with heavy rainfall, 5 times as many as the average. The same could happen in Japan. The country is considered one of the most dangerous in the world, and not just since Fukushima. And Tokyo, the world's largest city, is also considered the most vulnerable. 35 million people live here at extremely close quarters. And the city is susceptible to all sorts of natural disasters. The quake in 2011 once again reminded inhabitants that the Japanese capital is sure to have its own big one. Typhoons thrash the country, bringing public services to a standstill. These events regularly submerge whole areas in floodwaters, claim lives, and cause damages in the millions. But Japan wouldn't be Japan if it didn't meet the challenge with a technological solution. A gigantic installation reveals itself 80 meters underground. Here, under the project name GCANS, a subterranean concrete cathedral was built to outfox deluges that would otherwise flood streets and houses in a tropical storm. 4 rivers run through the region. Before they can jump their banks, the water is channeled into a spiral-shaped cylinder, which also decelerates the speed of its flow. From here, the floodwaters flow into a system of 10-meter-high pipes into another cylinder. The water masses then rise until they reach the rim of the giant cathedral and then fill it up. Powered by turbines, huge paddle wheels pump 200 cubic meters of water per second into the Irogawa River, from where it flows on into the Pacific. Rapid urbanization of the water-rich region, which lies below sea level, meant that the water could no longer be absorbed and regularly jumped its banks, where it caused major damage. Sri Lankan specialist for water safety and climate change, Srikanta Herat, participated in the design of the facility.
Now, if you take Japan, it's subject to so many different hazards. You have earthquakes, floods, volcanoes, tsunamis, and so on. So from the beginning, the Japanese culture is that if you give in to each of these, there will not be much left. So people have to live in a very limited, flat, narrow land, which is in the coastal areas. And that are the urbanized areas where we get the majority of the people living in. So on one hand, there are multiple threats. On the other hand, there's not much places to go.
But Herat is convinced that mega technology can no longer be the only response to natural disasters. He believes Fukushima has led to new attitudes and approaches.
So when you are subject to something, you build stronger to withstand that. So you keep on building your resistance against the different types of disasters. So because of that culture, I think it's possible to come up with these schemes and implement them, because to guarantee safety at a certain level. But I think this is also changing rapidly now after the March big earthquake, tsunami, and the nuclear disaster. At least that's now clear identification that we have to treat different types of disasters differently. The one which happen very frequently and one which happen very infrequently. And we can't control everything.
Impoverished countries like Bangladesh cannot even contemplate implementing such astronomically expensive technology. Here, people have no choice but to endure the violent vagaries of nature. When in 1970, a horrific cyclone raced over eastern Pakistan, it swept almost 500,000 people to their deaths and went down in the annals as the worst storm disaster in recorded history. 10-meter-high floodwaters submerged large areas of the islands in the Ganges Delta. Outrage over miserable sanitation and deficient aid efforts by the then government finally resulted in the succession of Bangladesh from eastern Pakistan. It remains a sovereign nation. Bangladesh lies just a scant meter above sea level. Its rise will pose a serious threat to the country and to many other coastal regions worldwide.
This is a hurricane, the greatest storm on Earth. Today, with the help of the weather satellite, radar, and reconnaissance planes, we are better warned than ever before when hurricanes approach. People can prepare, but that is all.
In the early 1960s, the U.S. government started a research project codenamed Storm Fury, aimed at diffusing the force of hurricanes. The scientists scattered silver iodide in the rain bands of the storm to dissolve the inner structure of the hurricane. The target was the cloud layer just outside the actual eye wall. By seeding these clouds, it was thought that a new, larger ring would be formed around the eye, thus weakening the hurricane. The experiment was conducted over the open seas, far from any landmass. But the results were so disappointing that Project Storm Fury was shut down. But the weather makers didn't just throw in the towel. In 2005, the Wyoming Weather Modification Project was started in response to the extreme drought that had plagued Wyoming for several summers running. The clouds here are still being seeded with silver iodide, but this time in winter. The silver iodide allows the ice crystals in the clouds to keep growing until they drop down. The depth of snowfall shows the scientists whether or not the experiment has been a success.
I hear the assertion that we're playing God with the weather. No, we're really not. What we're doing is trying to nudge nudge nature to be a little bit more efficient and to put a little bit more down on the ground where we humans can use it, only for a short time before it's back in the atmosphere.
And since the project began, Wyoming has, in fact, seen about 10% more precipitation. Whether these little nudges really just harmlessly help to improve the weather remains to be seen over time. But history has again and again shown that the systems in which we human beings interfere, whether out of ignorance or irresponsibility, are usually much more complex than we expect. And what now seems like a blessing for the farmers could soon aggravate the situation, possibly completely destabilizing the system we call weather. The People's Republic of China openly manipulates the weather for parades and state occasions. There is even an official weather modification office, responsible, for example, for delivering clear skies for the October 1st National Founding Day celebrations. Each year, tons of chemicals are sprayed beforehand to squeeze the clouds dry. Likewise, nothing could be left to chance in 2008 for the opening ceremony of the Olympic Games. An incoming rain system was intercepted well outside the capital, and the fireworks display went on to dazzle without disturbance. Every year, the Chinese cough up the equivalent of $60 to $90 million for weather modification. Sometimes they shoot wide over the mark. In a November 2009 attempt to combat drought, the authorities inadvertently triggered a snowstorm that plunged entire regions of China into chaos. But worse things have happened. In August 1952, the British Royal Air Force carried out Operation Cumulus. Clouds were seeded with dry ice. Only 30 minutes later, those clouds dropped their wet payload. But the research data was immediately classified and vanished into secret British military archives. It happens that on the same day, Lynmouth in Devon was hit by one of the worst floods in British history. After extremely heavy rainfall, the Exmoor River suddenly and violently burst its banks, sweeping away homes, bridges, and businesses. 34 people died in the disaster, which was officially deemed an act of God. 30 years later, the seemingly harmless research files were finally released, but the fact that they had been classified immediately following the disaster is evidence that the Air Force believed human interference had had a hand in it. After all, it's no secret that the military research labs of many nations are busy trying to weaponize weather. But winds and storms are not only destructive. When a sandstorm rages in Chad, the giant trees in the Amazon thrive. About half of the global atmospheric dust comes from the Sahara. The majority of it is supplied by the Baudelaire Depression in Chad and consists mainly of dead algae from the sediment from the shrinking Lake Chad. Trade winds carry the dust over 5,000 kilometers westwards across the Atlantic, about 40 million tons of it a year. Vast amounts of tiny fossilized algae from Africa fertilize the huge trees, mainly with phosphorus and iron, causing them to shoot up. The Sahara is, so to speak, range in chief of the Amazon rainforest. Even in Hawaii, phosphorus has been found that can be traced back to the Sahara. But the fertilizing effect can also get out of hand. Iron is very rare in the world's oceans. The deficiency of it limits the growth of algae and bacteria. When the iron-rich dust falls into the sea, it can lead to the red tides that claim the lives of numerous fish and shellfish. The algae also influences storms. The red seawater warms up more than the blue, thus supporting the formation of hurricanes. The cycle is complete. For millions of years, winds have shaped the face of the earth. Wind erosion can eat away at cliffs and even grind down entire mountains. Thus, landscapes and habitats continually come and go. Sandstone consists of layers of various degrees of hardness, which allows it to be shaped by wind into fantastic rock formations, like here in the Grand Canyon. Among the most famous are the fairy chimneys in Cappadocia in Turkey. The Australian pinnacles are the remains of old dunes, limestone deposits built up in the root canals of dead plants that stretched deep down into the ground. The wind later exposed them. German meteorologist Andreas Fink is on his way to join a group of international researchers in the Sahara to examine the wind in action. The wind-whipped desert dust over the Sahara means that the weather satellite maps show the region as basically a white patch. Within this white patch, the scientists expect to find a previously virtually unknown phenomenon: huge heat blisters billowing over the desert.
The heat-induced low-pressure system over the uninhabited Sahara is the engine driving the West African monsoon, and it brings West Africa either a biblical deluge in some years or a drought. It's these cycles we want to understand to enable us to warn people better in future.
June 2012. The aircraft of the Fennec project is departing from Fuerteventura. Having arrived at their destination above the Sahara, the researchers fly at an altitude of just 150 meters above the desert. It's the only way they can get the necessary data. The thick veil of sand makes satellite observation impossible. But precise data is extremely important for the people of West Africa, because although the summer monsoon season brings life-giving rain, its exact time of arrival, duration, rainfall volume, and interruptions cannot yet be predicted. One of the biggest challenges of the Trans-Saharan flight is that the key area is in the middle of nowhere.
To facilitate an airborne campaign, we have to fly for 2 hours before we can get to the region we want to measure, which means we have to be very accurate with our planning, because if we can only fly for 2 hours, that means for 5 hours, we've only got 1 hour to make our measurements in this region. So we've got to make sure that we get to exactly the right place. So we have a forecasting team back in the operations centre communicating with the aircraft, the satellite phone systems, and they're sending the latest satellite images to the aircraft so we can modify our route so we can get right into the centre of a dust storm, for example.
Low the researchers are chasing can cover an area the size of Europe. Over the course of the year, it migrates to West Africa, bringing cold air sucked from the Atlantic to the African continent. The flight altitude depends on where the dust is suspended in the air. Newborn sandstorms carry along huge amounts of dust. After a time, it begins to drop. It is this transition that interests the researchers, when the big particles clear off and only the tiny particles, which can travel great distances, remain. Step by step, they fill the gaps in knowledge, which will hopefully lead to more accurate forecasts.
These days, a 5-day forecast is as reliable as, say, 20 years ago, a 1-day forecast. So we're trying to get as good a forecast as possible for Africa, and that's important globally, but from an African perspective, it's very, very important because it helps them to predict when the monsoon is going to happen, and the monsoon is very important for people planting crops.
The global warming that keeps ramping up the weather machine makes forecasting increasingly difficult on the one hand, but all the more vital at the same time. Because although we influence the global climate, we are not in fact able to shape it to suit our needs. All we can do is to try to get prepared and to react accordingly. And the dust could play a decisive role, because many models don't yet factor it into atmospheric temperature calculations. But this dust keeps a portion of the solar radiation from reaching the Earth, so it is not warming as much as expected. That's a regional effect, but the dust blankets that fan out across the Atlantic also affect the climate in ways that still need to be further studied and better understood. Another great unknown in the system we call weather is lightning. Although it's one of the longest researched weather phenomena, the laws of physics that govern it have not yet been thoroughly studied. Florida Institute of Technology physicist John Dwyer is especially interested in the high-energy radiation generated by the discharge of lightning.
Florida is a great place to study lightning. We're a long peninsula between warm water, and so we get the colliding sea breezes which cause things like that. Now, we could wait for natural lightning, we could wait for something like that to come overhead, but that might mean waiting all summer. It's much better to bring the lightning to us, and so we use things like this. So this is a rocket that has a spool of Kevlar-coated copper wire behind it.
Dwyer uses this rocket to chase after lightning. From a military testing facility in Camp Blanding, Florida, it is shot 600 meters into the sky during a thunderstorm. Copper wire attached to the ground acts as a lightning conductor. Near the launch ramp, a photo detection device measures the radiation from the lightning. High-speed camera images show for the first time that extremely strong electrical fields are formed during the milliseconds of the lightning flash. The gamma rays that can be generated by the lightning represent a serious threat to air traffic.
If an aircraft were absolutely in the wrong place at the wrong time, right in the center of a thunderstorm when it was making one of these gamma ray flashes, it's possible that the doses could get quite large. You could, in principle, receive almost a lifetime's worth of radiation in less than 1,000th of a second.
Astrophysicist Gerald Fishman discovered the gamma ray radiation from lightning more or less by accident in 1994. When taking extraterrestrial gamma ray measurements. Until then, no one had imagined that lightning could generate nuclear radiation. But lightning isn't the only danger that big storm cells bring. When they start to twist and turn, tornadoes leave a swath of destruction behind them. Tornadoes do not cause the kind of widespread devastation wreaked by hurricanes, but the destructive force visited on the spots where they do strike is all the more terrible. The most dangerous of them occur in Tornado Alley in the U.S. Midwest between the Rocky Mountains and the Appalachians. Here, the cold air from Canada meets the warm air from the Gulf of Mexico. In the state of Kansas, 95% of the town of Greensburg was destroyed. Eyewitnesses describe a sinister cloud that sunk down and touched the ground. It appeared out of nowhere, and suddenly the houses around them seemed to explode. Minutes later, it was all over. In San Francisco, tornadoes are so rare that no one worries much about them. The locals here have a more pressing worry, namely the big one, the major earthquake that is due to hit for sure, sometime within the next 20 to 30 years. But the city and the whole region does in fact face another threat altogether, a superstorm of the kind that strikes the area cyclically every few hundred years. The Arc Storm, as it's called, will bestow on California a flood disaster of biblical proportions. Every 100 to 200 years, an arc storm pulls huge volumes of warmth and humidity out of the Pacific tropics and sweeps with monstrous force over the west coast of America. This causes a series of atmospheric rivers to form that can lead to weeks of heavy rainfall. Rivers would jump their banks, streets and bridges crumble. Everyday life would come to a standstill. Researchers at the United States Geological Survey estimate damages at $725 billion, 3 times as much as predicted from a devastating earthquake. During the last arc storm in the winter of 1861-62, it is said to have actually rained a biblical 40 days and nights on end. Geological evidence indicates that that was not the worst episode. Some arc storms in the distant past were far more disastrous. It is impossible to predict when the next one of these storms will occur, and as with the expected big one, there is no way to prevent the next arc storm from happening. All that remains for people to do is to prepare as best they can for D-Day. Theoretically, the same scenario is possible in Europe.
These rivers of condensation, the arc storms, are also present above the Eastern Atlantic and Western Europe. It's certainly conceivable that in future weather conditions will arise in winter in which an arc storm causes it to rain for days and weeks on end. And it could come to extreme flooding, for example, in the Rhine catchment area.
Though we can't yet speak of arc storms in Germany, recent heavy flooding, such as that in the Oder-Neisse region, shows how vulnerable the cities and thus the people here are. Suddenly, climate change is no longer just a word and something that happens on the other side of the world. With its storms and floodwaters, it has long since come to the streets and houses of Germany. German civil defense has reacted by forming an alliance of relevant authorities to be able to react effectively to the coming challenges. The plan is for key areas such as critical infrastructures, energy, water, and food supplies to be managed in a coordinated manner across departmental and state lines.
According to latest insights, we will experience a significant increase in heat waves, extreme rainfall, as well as storms. So our civil defense systems have to prepare for it. For example, we need to speed up our warning systems. We will see extreme weather events limited to certain regions, which means our warning system should be adapted accordingly. We also need to strengthen the self-help ability of the population. Everyone should be able to help themselves to a certain degree, because government assistance might not arrive in time.
Tornadoes are no longer a rarity in Germany either. Between 20 and 60 such twisters are visited upon the country every year. They appear suddenly and without warning in the middle of Germany, leaving a trail of destruction in their wake, such as here in Micheln, in Saxony-Anhalt. And even other, previously virtually unknown weather phenomena could soon become a regular occurrence in Germany. In April 2011, extreme aridity coupled with sudden gale-force winds caused a sandstorm that swept across the Autobahn near the northeastern coast between Rostock and Güstrow, causing a massive vehicle pileup that killed 8 and injured many more. Authorities have expressed concern that such incidents could become more common. Most reputable scientists are agreed that climate change will take a drastic toll on our lives. Storms will become more frequent and more ferocious, with correspondingly dramatic consequences. There is not a shred of doubt that global sea levels are rising. Calculations vary, but a rise in this century of between 50 and 100 centimeters is expected. That will lend every storm surge even more destructive power. Latest estimates predict that by the year 2070, the world's major port cities will face a 4 times higher risk of being hit by a flood of the century. Whether the storms get stronger or weaker, occur more or less frequently, whether we human beings exacerbate them or not, it appears we will never be able to control them. We have no choice but to beware and protect ourselves as best we can, because storms will always be a fact of life on our planet.